We were discussing the different strategies to be adopted for designing embedded systems. In the last class, we have looked at design requirements, and then we had started looking at modeling tools. We have discussed basic features of UML, Unified Modeling Language, which provides us with an object-oriented representation scheme for specifying the design. We shall continue on usage of UML for designing real-time and embedded systems. In fact, UML, if you see, is a kind of a all-encompassing design language by which you can represent both hardware as well as software components. In fact, UML for real-time systems is about applying UML for designing real-time and embedded systems. So, one of the basic issue related to that is the different architectural models that are part of UML language for specifying your design. You can specify your system and subsystem architecture, the distribution view, resource and concurrency view, safety and reliability view, as well as deployment view. These different views we shall discuss today and consider their relevance for designing real-time as well as embedded systems. At a top level, we have the view of an embedded system as a system. Okay? So, this is a representation of what we call a system level architecture. Okay? So, in a sense, if you look at this diagram, this basically represents a kind of a encapsulating class which represents the system as a whole. What we have shown here are different kinds of actors. Actors are entities which would interact with the system. If we are talking about an air traffic control system, then there would be aircrafts. So, with respect to one air traffic control, there may be many aircrafts, because many aircrafts will be controlled by one air traffic control. Then there will be the primary radar, secondary radar. These are all actors because they are standalone systems providing data to your air traffic control system. Similarly, there are controllers who will actually take the decisions. Then airspace system, which may be the global manager who has got the global picture of the airspace, and the flight planning system which would plan the paths of different flights. So, this way we can represent the top level view of an embedded system. So, once we start with this top level view of the embedded system, we should go into the details. Okay? So, using the basic principle of top down refinement, we can go into the details. So, the details will give us what is called subsystem architecture. So, subsystem architecture indicates the different subsystems which actually forms the overall system. So, here what we have seen is that aircraft space subsystem is one subsystem. So, you have got radar subsystem, antenna subsystem, so on and so forth, alarm subsystem, and what we have indicated here is that these are all stereotypes, stereotype subsystem. And this 1:1, this 1 at the two ends of the link is indicating there is a class relationship of one class being linked with one of these classes. Okay? So, radar subsystem will provide the interface with the external radar for getting the data and managing the radar depending on the requirements, and this will provide the data to the main aircraft space subsystem. So, you can have a number of such subsystems. Now, what is the advantage of doing this? You can now look at designing of these subsystems individually, okay, and look at their details. Related to this is what is called a collaboration architecture. In fact, collaboration architecture tells you how exactly the different components collaborate with each other. Say for example, if we look at the separation distance as a parameter, so this separation distance is related to the two aircrafts, because we shall be measuring the separation distance between the two aircrafts, and this object, if we consider this as an object or as a sensor or as a hardware element which is monitoring this distance, it will generate what? An alarm if the distance is less than a threshold. Okay. So, that is why the alarm object is related to this separation distance. So, this is representing the collaboration, and in fact, you will see that from alarm you actually have the view which is getting generated, and these are again actors that we have shown here. You have got a radar as an actor, air traffic controller as an actor. In fact, when we took a top level view of the system, the requirements or the functionalities desired by the actor actually specifies the functional requirement of the system. Depending on that functional requirements, we had come to the subsystems, so that subsystems can cater to individual requirements, and then we have linked up through this collaboration architecture these subsystems objects, because one subsystem cannot act independently, it has to make use of other subsystems, and that is why we say the subsystems collaborate with each other. Okay. So, the subsystem collaborate with each other, and this collaboration architecture is represented through these kind of a diagram. Okay. So, here you find that radar. So, radar has got linked with a radar controller, that is linked with your tracker which tracks the aircrafts, and then this is part of your track manager. Okay. Now, similarly, there is an alarm manager which is where alarm is linked with. So, alarm will be component used by the alarm manager. Next we come to distribution architecture. So, once we have got top level view with respect to the requirement analysis, we have got the top level view. From top level view we have got the subsystems, we have got the collaboration view, and next comes the distribution view. The distribution view tells us how the objects are to be distributed among multiple processors and their communication links, because your embedded system did not consist of a single processor. Your air traffic system, a complex system like an air traffic controller system, will not be built around a single processor. There may be multiple processing elements, and there would be policies for managing communication link, the communication protocols, communication quality of service management. So, all these things can be actually specified through your distribution architecture. Then comes the safety and reliability model, because air traffic control, I cannot permit air traffic control to fail. So, there has to be safety and reliability issue. So, that safety is freedom from accident, and the reliability is the ability of the system to work without failure for a large period of time. And safety and fault tolerance requires some form of redundancy. So, when we are designing for safety and fault tolerance, our design specification should depict these redundancies. So, here is an example. So, what we say, this is an actuation channel 1, this is another actuation channel 2. In fact, if you look into this diagram, this is representing an object, and the object is consisting of, these are actually components. In fact, this notation is for indicating what we call the components in UML notation. So, components can be piece of software, components can be even hardware realization, can be even a kind of documentation if it is so desired. So, here what we are showing is that different components, input processing, data transformation, data integrity check, output processing, all these put together forms your actuation channel 1. And for the purpose of redundancy, you have indicated that there will be another actuation channel, okay, and they will both be connected to, here I have got an actor, this is a monitoring data source. The monitoring data source will feed both the actuation channels, and these actuation channels will feed the actuator together. Okay. So, even if one of them fails, okay, other one can work. So, there is an inbuilt redundancy and fault tolerance in the system. So, the specification for redundancy and fault tolerance can be provided through this kind of safety reliability model. Next thing comes is the concurrency model. So, we have seen that we need to identify the concurrent tasks depending on external world and its requirements. So, concurrency model refers to identification of task threads and their properties. It tells you how to map passive classes to threads, identification of synchronization policies, task scheduling policies. An unit of concurrency is what we call active objects. Active objects are again stereotype objects. So, therefore, if you look into it, that when we are specifying the overall behavior of the system, what we said, we shall use a state transition diagram to specify behavior of the system. But when there is a concurrency, there would be what? A concurrent set of state transition diagrams depicting the behavior of the system. Okay? Now, how, therefore, if you look at an FSM, FSM may represent one aspect of the system, and when we want to actually consider the concurrent processing aspects of the system, we should use the concurrency model to depict that concurrency aspect. So, simple approach is that of using what we call an activity diagram. Okay? So, in fact, this activity diagram is similar to your, in the look, it is similar to your state transition diagram, but it is not state transition diagram. What it says, it actually gives you a set of steps, sequential steps. In fact, if you see, this diagram tells you how to do the concurrency design. So, what it says, that apply task identification strategies. Okay? So, that means once we have the requirement specification done and we have got the top level view of the system, with respect to the top level view of the system, we should try to identify what are the different tasks. Okay? Then you construct active object for each of these tasks. In fact, these active objects can also translate to the subsystems in the global system. Okay? So, you construct active object for each, add passive semantic objects into active objects via composition. Because why passive semantic objects? There may be components which are to be controlled within a task. Okay? So, there may be a LED indicator. Okay? So, an LED display or LCD display will be a passive object under the control of a task. Okay? So, I can put that task as part of your active object through composition. That means, it forms what? Basically a field in that active object, because it is a component of that active object. Then you define your collaboration, because collaboration is collaboration between different objects. So, depending on how the objects have been mapped to active objects or threads, you will be modifying the collaboration. Then you refine scenarios. What are scenarios? Scenarios is the situations in which these concurrent tasks need to work and act. And what are really scenarios? Scenarios will again come from the requirement analysis, because requirement analysis tells you the different conditions under which the system is expected to operate. And then you can have two parallel, this is actually represents the concurrent activities. Okay? In fact, this activity diagram, when there is a vertical line and there are two branches from that vertical line, this actually represents the concurrency concurrent task threads. So, test by scenario execution. So, once you have the scenarios, okay, you test each of the tasks by scenario execution and apply the schedulability analysis. That is, whether the tasks can be scheduled. If it is scheduled, then what are the constraints the task should satisfy. In fact, what kind of execution times the task should meet. So, that will again dictate your choice of the processes. So, in fact, this is an activity diagram, and this activity diagram through this kind of concurrent paths actually depicts the set of concurrent tasks the system should really handle. In fact, the more detailed depiction of concurrency comes via what is called task diagrams. Task diagram shows only those model elements which are related to the concurrency model. Active objects, so active objects are objects associated with threads, active threads for execution. Semaphore objects, message and data queues for communication between these threads, as well as the constraints. These constraints would be primarily schedulability constraints. So, let us take an example. So, here if you see this task diagram is typically similar to that of your collaboration diagram. In fact, this is representing the different classes and it is also representing the links between the classes, okay, how they are linked. But along with it, you will find there are interesting additional informations which have been provided. Here, you have actually provided the schedulability constraints, the periodicity, because this is if this is an active object, I have indicated by this stereotyping that this is an active object. So, since it is an active object, the thread corresponding to the active object should satisfy the schedulability constraints. Okay. So, you have specified what are the schedulability constraints. The period has been specified, worst case execution time has been specified and deadline has been specified. So, these details have to be represented so that your specification becomes complete. Similarly, if you look at here, what you have got a queue, a data queue. Okay. So, I have represented a data queue for the purpose of communication with other objects, and a data queue, if it is a data queue which is being used for communication between multiple active objects, that queue has to be synchronized, because two processes cannot simultaneously access that shared data object. Okay. So, you need to have synchronizing primitives like your semaphores. Okay. Semaphores would ensure that only one process can access the shared memory. So, that semaphores have to be associated with this kind of shared memories. Okay. So, here this is queue is a shared memory and you have got a mutex which is actually actually belongs to the this stereotype of semaphore object. Mutex is a semaphore object and that is associated with this data queue. Okay. So, how these concurrent active objects have to be managed in terms of their schedulability constraints, how these active objects would communicate with each other via shared memory, and what kind of synchronization primitives to be used to manage access of the shared memory is depicted through this task diagram. Okay. So, next comes the deploying the system. So, the deployment diagram shows the configuration of runtime processing elements and the software processes living on them, and the deployment diagram visualizes the distribution of components across the enterprise. If it is a distributed system, it has to depict that depiction as well. Okay. So, if you look at that, so what you have got, this is an example of a deployment diagram. So, this is basically an object. So, this is indicated as your stereotype device. Okay. So, on a device a particular set of objects have been mapped. Okay. So, this is basically your server. Your database can be located at a remote point and connected via maybe a JDBC call. Okay. And this is the mainframe which may provide you with the actual access to the system, which can provide you the basic access to the system front end, which is again a device. Okay. So, I am just showing a deployment diagram to illustrate how the different tasks gets mapped, how different objects gets mapped. So, this is your basic application server. Okay. This can be your mainframe for processing as well as access, and this is basically your database. Right. So, this this is a way in which you can actually represent even a distributed embedded system. Although this application or the example that I am showing here is not strictly an embedded system, it is a kind of a general a computational distributed computation application. So, what you can therefore conclude by looking at UML, UML provides you with a modeling tool by which you can provide the top level specification of the system. Okay. You can start at the top level view on the basis of the requirements. The requirements come from the actors of the system. The system architecture or the system level view gives you the top level view of the system. You can identify the tasks corresponding to the system. You can decompose the system into subsystems. Subsystems can be further decomposed into constituent objects. Now, depending on the concurrency model, these objects can be mapped onto active objects. You can specify the schedulability constraints for the active objects. You can specify how these active objects can share memory. You can specify the dynamic behavior of the subsystems using state transition diagrams. You can also use the sequence diagrams to show how the messages can be passed between the objects for the purpose of realization of its behavior, expected behavior. So, in summary, what we can say is that the UML provides a kind of a complete specification tool for specifying the functional as well as component wise architecture of the system. Okay. Now, if we come from here and look at other kind of tools, we will find that there are other tools which are targeted for various kinds of specific applications. Okay. In fact, when we say that we are using UML as a modeling tool, formally we are not distinguishing between objects which may be physical hardware objects and software objects per se. We can distinguish them subsequently, but when we are designing the system, we may not distinguish them at the beginning itself. Okay. There can be objects or the systems obviously which will have part of it implemented in the hardware, part of it in the software. Okay. Now, those objects, if we think it in terms of their actual implementations or the translations, we would need different kinds of specification tools. In fact, if we look at even a standalone system, okay, for them as well, we would like to have tools through which I can specify both hardware and the software aspect. In fact, System C is one such tool which had been developed around the language C++. So, what we say that functionality of many systems or subsystems is a mix of hardware and software components. In fact, that is what we had seen if I specify a complete architecture using UML notation. And the simulations would require an interface between hardware and software simulators unless the same language is used for the description of hardware and software. So, this becomes a constraint. And System C attempts to describe software and hardware in the same language. So, if I have identified a subsystem or an object, okay, whose functionality I would like to describe. So, if I describe that functionality in using a modeling tool like System C, I can describe both software as well as hardware using the same language. In fact, that is the basic motivation for developing this tool called System C. So, System C in a way is a system level specification language and captures system behavior. So, what are the features? It based on C++ programming language. So, it satisfies the advantages and the properties of object oriented design. So, C++ capabilities are extended to support hardware description by providing a library, provides as part of the language a simulation kernel. Why this simulation kernel is required? Because you have to simulate the hardware to execute the software. Okay, so if you say that the first point we said that if we have hardware and software different, then that simulation time interface becomes critical. So if you have a simulation kernel, then what we can do is we say we can do a co-verification. That means I can verify my software along with the hardware that I am designing. And it provides a flexibility to use standard C++ programming development tools. So what is the design flow in that case? The system is being specified using system C. So system C provides executable specification. Okay? So just think in terms of your UML notation. In an UML notation, you have identified a class, fine. You have identified the methods, you have identified its fields. Now that class has to be actually implemented, and I can actually use maybe system C to encode that class, and when I am encoding it, I am encoding both hardware as well as software. Okay? And what I get an executable specification, because that system C code can actually be executed, compiled and executed. Compiling and execution of system C code will mean what? Will actually mean execution of the software with the simulation kernel, where the simulation kernel is simulating the hardware. Okay? So once we have these executable specifications, so therefore that gets partitioned into hardware and software blocks. And a software developer can use C++ simulation environment, which can be used for developing as well as testing the software. So what are the basic concepts involved in system C? A system is modeled as a collection of modules, and modules contain processes, ports, channels, and even other modules. Okay? Processes define behavior of a particular module and provide a method to express concurrency. Okay? A channel implements one or more interfaces, where an interface is simply a collection of methods. A process accesses a channel's interface via a port on the module. Okay? So what is the implication of this description? So I am modeling a system or a subsystem as a collection of modules. Okay? The modules contain processes, ports, channels, and even other modules, because it can be composed of sub-modules. Okay? And the processes are actually what? Intuitively, processes provides me with the specification of what the module is going to do. Okay? It has got ports. Ports will be for communicating with other modules. Okay? And processes define behavior and provide a method to express concurrency. In fact, the moment I express this concurrency, now this concurrency can be actually implemented, maybe implemented in hardware. Okay? So this is the flexibility and the facility that this module would provide you. A channel implements one or more interfaces, where an interface is simply a collection of methods. Just like any object, when we have an object, what is an interface of an object? It's basically its public view, because you actually use methods, okay? And these public methods provide the interface to use the features of the object. So a channel in this case of a module provides that interface. So a module can be actually a hardware module, and what we are talking about here, if you can see, that encapsulation of the entire hardware module through an object oriented paradigm. A process accesses channel's interface via a port on the module, okay? Because process has to access the methods. If it is collaborating with other modules, it has to use those methods. So, accesses channels interface via port on the module. So, basic modeling constructs therefore would be module. So, you need to have a feature to define a module. So, a module is defined as, this is SC System C module, and module has got a module name. A typical module, as we have already shown and talked about, discussed, will have ports for module communication, processes as well as submodules. And a process is declared within a module, right? And there can be three types of processes in System C. So, because processes, if you see what is interesting, I am talking about a method, and method is a process name actually. So, process is declared in a module, and this process, in a way, if you want to do a mapping, this process is mapped onto a pure software based object. If you look at class, a process is nothing but a method, okay. But in case of a module, I am calling them as a process, a method as a process. So, if I declare a process as a SC method, what does it mean? This process cannot be suspended, and the process executes when triggered by a sensitivity list. Okay. Sensitivity list means there may be sensitivity list may translate to external signals to which the process is linked. That means you can imagine that this can be an action which would take place when a particular signal is true or valid. Then you have got what is called thread. Okay. Thread process name provides you a process is declared as a thread. Okay. When a process is declared as a thread, it is possible to wait for events within the process. Okay. If you remember the previous case, what we said, that the process cannot be suspended. It is triggered by the sensitivity list. Once triggered, it cannot be suspended. But when we have a thread, it is possible to wait for events within the process, and process executes again when triggered by a sensitivity list. So, this aspect of its behavior is same as SC method, the other one that we have discussed. Then you have SCC thread and a process name. A process declared as a C thread is a clocked process. So, that means you can understand, therefore, what is happening here? This is actually a process. Process means a set of actions. This set of actions is synchronized with respect to a clock. So, I am actually providing a description of the hardware through these methods, and actually a module would be nothing but in a way a hardware, okay, with the ports providing the channels for communication. Please note the word channel that I have used not in the sense of System C, but in a English generic sense. So, processes communicate with each other through signals. Okay. So, if I say ports of modules are connected via signals. So, this is your module 1, this is your module 2, and these modules have to be connected, they have to be connected via port, okay, and there will be signals connecting the ports. Okay. And these are, if we consider these part of a bigger module, module EX3, which consists as part module EX1 and EX2, then these are the ports for communicating with the external world. Okay. So, you can see that how you are actually describing really a hardware using an object oriented language. Okay. Along with it, you can even describe the software as well. So, this is the basic advantage of your System C, right. Let us take an example. This a module. So, if I look at this module, so this structurally what we have these input signals, input ports being specified. You have got these methods, these are all processes, okay, and these are the child process, because there is a module which is part of this module. So, a method, okay, it can be a method or a thread process, that is a process which is defined in this child module will be actually a child process, okay, and these are the outputs, okay, which is going out. This port is a in out port. That means I can have an input as well as output. So, effectively what I have done, I have got a specification for the hardware. Okay, I have got a specification for the hardware. Now, let us take an example, a simple half adder. All of us are familiar with the concept of a half adder, and what we are looking at here is basically very simple system C construct for describing the hardware. Okay. There are complex constructs which we are not going into. Okay. We shall just look at the basic features of system C by which you can describe a hardware. So, here we are defining a module which is a half adder. Okay. Now, it has got, these are input ports, Boolean ports, let us say A and B, then output ports, they are also Boolean, sum and carry, and in fact, you have also support for data types. A programmer can use the data types, and there are also hardware specific data types which can be used in your program. Now, you have got this process, because module has got a process. So, that process is half adder. Okay. And what you are doing is, you are declaring this SC method half adder, because half adder is a combinational circuit, it cannot be suspended. Okay. And it is sensitive to what? Sensitivity list would contain two signals A and B, which are your input signals. So, the moment I have got input signal A and B, I shall be computing the addition, that is your SC method half adder, the process, and that cannot be suspended. And if you look at here, this half adder, the method is basically defining the logical function for sum and carry. Is this clear? So, I have actually specified the hardware, and this is what I have referred to as process implementation. Okay. Now, in fact, if you look into that system C, as I had started with, the basic concept of system C is that for providing a specification language, an executable specification language by which you can describe your software as well as that of your hardware. Okay. So, I am referring to these as a system specification language. Okay. Please keep in mind is that system C is not just a hardware description language. Okay. So, what it implies therefore, that if I am coming from a top level design, if I have identified an entity which can be translated to both hardware and software, I would like to have the hardware software partitioning, describe the hardware as well as software using the same executable specification, and then what do? I actually compile, run. So, I have got a co-verification, and then I would go into actual physical translation, that is actually building the hardware component and then trying to have the software maybe running on it as the requirement may be. Now, we shall look at another language which is your VHDL, which is again a modeling tool. But how VHDL is different from system C? VHDL is purely a hardware description language. Now, what I have tried to provide you with, given the constraints of time, the flavor of modeling tools which can work at different levels of abstractions. Okay. UML is at the top level modeling tool. Then you have got a system C, which is a both software hardware specification. Now, I am referring to VHDL, which is a purely hardware description language. Okay. So, it describes architecture and behavior of discrete electronic systems and primarily to be used for modeling system hardware. And in fact, if we talk about the hardware, there are multiple levels of abstraction with which we can look at hardware. At the top level, what we call the behavioral level, which is a functional description of the hardware model. There may be no system clock. you want to create the basic stimuli, and this is simulatable. That means I can simulate, I can have a behavioral simulation, but I cannot really synthesize, because until and unless the timing constraints are known, I cannot synthesize. What does synthesis means? Translating this functional specification to actual hardware blocks in terms of gates, and even at the lower level in terms of actual transistors and their implementations. So, next from the behavior level we come to what is called register transfer level. Okay. At a register transfer level, we specify the activity in terms of combinational logic and storage elements. We specify the system clock, okay, because if I am having storage elements, would be actually flip flops. Okay. So, why it is register transfer? Because I can specify behavior of the circuit in terms of data transfer between the different registers, and while the data transfer takes place, the data gets modified or transformed using your combinational circuit. That is exactly how you have designed your digital circuits. Okay. If you think in terms of designing an FSM, what does designing of an FSM means? You identify the states, you identify the flip flops required for the realization of the states, and then you require what? The input signals, okay, and you design the combinational circuit to provide the input signals that would cause the state transitions, as well as you identify the output signals that is required for driving your external circuit. Okay. So, if you look at from that point of view, your register level actually gives you a gate level or storage element level specification of the circuit, and that is there. Obviously, the clock is an important component. So, this register level specification actually gives you a simulatable as well as synthesizable specification. Next, it gives you a logic level, where actually you say that how the gates are connected, because let's look at this level. You can understand very simply. If I am talking about a register level, I am talking about a register. Register will be actually implemented maybe using a set of gates, because register is nothing but a flip flop. It has to be implemented using a set of gates. Gates will have different timing depending on the technology that is being used for implementation of the gates. So, when we come to the logic level, we actually provide the specification in terms of actual logic gates and the corresponding storage elements. So, the detailed timing can only come at a logic level, okay. And the layout level, it tells you physically how these transistors are put onto silicon, what is their interconnect pattern, and that will provide you the absolute detailed timing. Now, why VHDL is important for an embedded system designer? Obviously, for the purpose of designing hardware at an appropriate level of abstraction, and also at the same time to have the ability to use the core, because today if you remember when we discussed the processing elements, we talked about ARM, we talked about PEEK, we talked about other processors as well, and we said that these processors are available in the form of maybe soft core or a hard core. If it is a soft core, it can be a pure VHDL specification. So, when you want to add functionality to that processor, depending on your system design, you add on a module to the VHDL specification of the processor. Okay. So, you have got actually an enhanced hardware, fine. So, if it is a absolute hardware core, that means you may have actually the layout level design available with you. So, you add functionality to the system and maybe design an ASIC or a ASIP as the case may be. So, design flow, we say that VHDL editor goes through an optimization process. So, that gives you a device or place and route software, which would device fitting or place and route software, which is at the lowest level, which is device dependent. So, when you talk about a VHDL editor and provides a description of the hardware in VHDL, it is a behavioral description. From there you can derive an RTL specification, which is actually device independent. So, if you remember, if you say that I have got a VHDL description of a processor core and it is a soft core, because it is actually independent of its implementation, okay. And many of the designs of embedded systems built around this kind of soft cores being made use of. So, the design philosophy is you have a design entry, simulate, if it is okay, else modify, then you synthesize and optimize, again do the simulation, fine, and then do timing analysis and layout for coming to the final form. Okay. So, early testing, easy change of technology and structured system design. So, what you see that before even coming to the device level, which is coming here when we are coming to layout, we can do a simulation and testing of the system and to know its correctness. In VHDL, each design unit is called an entity. So, the designs, hardware designs are specified as collection of entities. Entities are comprised of entity declarations and one or several architectures, and each architecture includes a model of the entity. There can be various architectures. So, let us take an example. So, entity describes the interface or a black box. So, again if you go back to the half adder example that we dealt with in system C, here also it is in a way similar, but when you look at this entity, entity is telling you what? Simply the ports, ports A, B, these are in, and standard logic. This is a standard logic because VHDL can support multi-valued logic as per the standard. So, these are all standard logic. Sum and carry, they are out, they are also standard logic signals, and this is an specification of this entity, and this is a black box because we have not included what will be done inside this black box in this description. Then you have got in the black box what we have used, you have used port. Okay. So, ports can be in, out, buffer, in, out. So, if it is an in port, no signal update, out is write only, so there has to be a signal update. Buffer is read, but signal update, that means why signal update? Because the signal would change when it gets updated, and in out is a bidirectional data flow. So, these are the ports which are to be provided with an entity so that it can be connected with other entities. And when a port gets connected with other entity, the connectivity should be consistent in terms of the nature of the port. Okay. Then we come to what is called architecture. Architecture describes what is inside this black box. Okay. So, internal view of the black box, a description of the functionality of the entity is what the architecture provides for. It must be associated with a specific entity. One entity can have several architectures and contains concurrent statements. Okay. This concurrency can be because of the hardware as well. So, here if you look into it, this is an example of this adder, and this is architecture behave. In fact, this is a behavioral description of the architecture. What it says? It defines your sum, it defines your carry, and that is of end of behavior part of the architecture. I said that there can be various architectures. This is a behavioral description of the architecture. So, architecture bodies can have data flow description, behavioral description, structural description. Okay. The data flow description specifies how data will be transferred from signal to signal, and it can actually have concurrent statements because there can be hardware operations executed concurrently. Behavioral description is typically an algorithm because if you can use simple sequential code to simulate the behavior of a entity. Structural description provides a connectivity between the components and the subsystems, and it does not really have a description of the behavior. Let us take an example. It is a very simple tri-state buffer. Okay. So, what we are describing here are data flow description. Okay. So, this is the entity which was already defined earlier, and the data flow description is, if you see what it says, Q, this is a signal assignment, okay, that D signal is assigned to Q when N, that is enable signal, is 1, else Z is a tri-state. Okay. So, if you look at when means why it is a data flow model, because it tells you that when enable, if you consider when in a literal sense, it is associated with the concept of a time. When this signal becomes 1, then only that Q, okay, should be what? Representing D, otherwise it would be Z. So, it is a data flow model, it is not just a behavioral model. So, let us look at a behavioral model. In a behavioral model, what we are telling? For the same tri-state buffer, we say that if this is true, then this will be true. So, this is the, I am just specifying the conditions. I am not telling that when this is true, that this has to depict the value of D. Please note the difference between the data flow model and the behavioral model. I said it is more like an algorithmic description, so it can be run as a sequential code to do a behavioral simulation. Structural description basically tells you the structure. So, here what we have got is that two half adders can be put together to make a full adder. Okay. So, there are we have got components of top level full adder and two component half adder from the library, and I can use the signals to connect them. And the description would be like this. If you look at it, here I am describing the entity full adder, and architecture, then I am describing this architecture which has got the signals, okay, and the component is half adder with its port, which is AB input, sum carry as output. So, it gives you the description of this full adder in terms of components, and then the architecture, actual architecture, this is the definition part, architecture is U1 consisting of U1 and U2, which does a port map, okay, fine, and it is now defining the carry. So, this is completely defining my full adder as a connectivity between the two half adders. Okay. So, here if you see that half adder, this half adder doing a port mapping. So, what it is doing? AB, and I have got n sum n carry and this C in and n carry 2. So, these are doing a port mapping, because why this port mapping is required? This port mapping is required because if you look into here, this is the connectivity that I want to represent. The C in goes to here, okay, and this output here should come at this point. Okay. So, this is what the structural description is all about. Signals are specific type and they provide the interconnect between the different elements. Okay. And this interconnect tells you that how the signals have to flow. In fact, the signal assignment is through this symbol which we had already discussed, and this tells you that A is assigned to B. Now, process actually gives you what? Within an architecture contains sequential statements triggered by signals in sensitivity list. This is very similar to system C, and multiple processes can interact concurrently. So, this is a set of sequential statements, okay, and the sensitivity list comes from here. So, there would be concurrent and sequential statements. Boolean equations involving logical operators would be part of concurrent statements. They can take place in parallel. Conditional signal assignment, that is when this occurs, that is in parallel, and selective signal assignment, that select if there are multiple signals and select. So, these signals arrive in a concurrent fashion. So, that is why these are concurrent statements. Sequential statements provides a process structure. We have already seen if then else structure for defining the behavior. You can have case structure. There are also for loops to do a processing in an iterative fashion. Concurrent statements are executed all at the same time and outside a process. Sequential statements are executed within the process, and they are obviously order dependent. Okay. The process structure is executed when event on signal in sensitivity list is there and signals are updated at end of process. Any signals can be in list and process can be running or suspended depending on the case may be. So, if you look into here, this is a process structure, this is a label, this marks is a label. So, process is part of the architecture, okay, and this AB are the sensitivity lists, these are the signals, and this is, if you remember, this is the same. What I am doing, I am basically designing a multiplexer. So, if select is 1, then out Z is A, else Z is equal to B. Okay. So, I am defining this behavior through this process structure. There are wait statements. So, wait statements for coordination with the signals. There can be wait until a signal list. So, there can be wait until the signal arrives, wait until a condition occurs. There can be wait for specific durations. So, that means you can set a timer, and then when that timer expires, then actually the action takes place, and wait can suspend indefinitely. So, this wait can be put in the process statement itself and specify the different timing coordination between the processes. What is the semantics? Because once you have specified the model, the semantics actually tells you how it will be actually simulated. Okay? So, execution of a model consists of an initialization phase followed by the repetitive execution of process statements in the description of that model. An initialization phase executes each process once. So, basically this is the basic semantics. You start a simulation, assign new values to the signal, okay, evaluate the processes will now provide the future values for the signals because they will be connected. So, that value comes to the signals, and that way you simulate and activate all processes sensitive to signal changes. Okay. So, this way when you simulate, you can actually verify whether your hardware is giving you the desirable behavior or not. Obviously, there had to be more details to be looked at when you talk in terms of cycle accurate simulation. That means your timing conditions are taken care of accurately. So, but through this simulation you can actually verify your hardware. So, if you look at an overall evaluation of VHDL, it provides a behavioral hierarchy in terms of procedure and functions, provides structural hierarchy. There is no specification of non-functional properties, no object orientation. It is too low level for initial specification. In actuality, it is nothing but an assembly language for hardware generation. So, if we go through the complete chain, what we find that the top level specification comes from UML, System C gives you a combination of hardware and software, VHDL gives you a mechanism to specify completely your hardware. So, if we come to the summary, we have looked at the different modeling tools which can be used for designing embedded system. These modeling tools describe design at different levels of abstraction, and depending upon the task, modeling tools or their combination are to be selected. And now, in the next few classes, we shall look at this design task and how these modeling tools had to be used as part of these design tasks. We shall look at that.